So let's continue our discussion about work and rotational equilibrium. A few little things before I get started. Again, as a reminder, I'm going to be out next week. I'm also going to be out Friday. So as a result, this lecture is going to be a little bit longer. So what I'm going to do today is work some examples for you about torque and equilibrium that should get you through the rest of the homework that it's going to be due on Saturday afternoon, right? Saturday at midnight, I think. Also, I have posted a few things on Blackboard for you. The first is a video that I found several years ago. There's a channel called Smarter Every Day by a guy who's an engineer over in the North Alabama area. And he does science videos, that sort of thing. He recorded one about, that's 5 or 6 years ago now. It's maybe 10 minutes long, and it has to do with rotational motion, rotational inertia, and torque, which is going to be the next piece that we're going to look at is rotational inertia. But it has to do with why cats always land on their feet. And so he does some experiments with his cat. It's quite amusing, but very, very interesting and some good physics in there. Secondly, I have also, if you look under the content on Blackboard, I have posted a video for you that should help you start studying for the final test in this class. Next week, since I'm out, I'm going to post some supplementary videos for you that will get you started on rotational inertia, and we'll check it out when I come back, and I'll finish that up, and then we'll go on through the last few weeks of the semester. So having said that, remember what we've been talking about is this idea of torque and equilibrium. So remember, torque is kind of, it's another force that we have to worry about, right? Remember, everything that we do has been dealing with Newton's second law. This idea that the sum of the forces in a system has to be equal to the total mass of the system times its acceleration. Now, everything we've done up to this point, we've talked about things that have pretty linear forces applied to them. The things that we have applied forces that are in a rotational frame of reference, we've really done the same kind of thing, but we haven't really considered all those forces together. Well, what we're going to do now is we're going to have to start applying some of these rotational forces as well as the linear ones, all in the same system. So, for example, let's just get a good frame of reference, a good picture of what we're talking about. So here is, let's say we're looking top down on this thing. This is some kind of bar. It's attached to some anchor point here. And we apply some force F along this angle here. So maybe we've got a rope or something, and we're pulling, maybe this is a door, and we're pulling the door open using the rope. Well, we know that because we have this pivot point, right? This whole thing is going to want to turn that way. So that's going to be our torque, right? So what we have to do here is find a way to convert this kind of angular motion here into something more linear that's easier for us to deal with so that we can go set up our Newton's second law equation. Well, what we've said is that this twisting force has our torque. So this is the uppercase Greek letter tau that we use to indicate torque. So how are we going to find torque? Well, we know that we have this system here. So we've set up our kind of XY coordinate plane, and we're applying some force at an angle to it. We need to apply that force vector is infinite. So it might as well be drawn way back here, right? Or up here. It doesn't really matter. That's why we can do things on the free body diagram like through our pivot point. We make ourselves a nice little right angle there. Well, if you remember your high school geometry class, you will note that we have an angle on the other side of this plane. And our high school geometry tells us that those opposite angles have to be the same. So that's also theta. So what are we going to end up with here? Well, we're going to end up with some component vector here. We need one more piece of information before we can do this. We need to know the distance between our force and our pivot point. So we're going to call that distance R. So that means that this distance here, that's what we want to find. That is what we're going to call our R perpendicular. And we know, just doing some simple trig, since this is a right triangle, all we've done is rotated the right triangle, right? So we've still got a right triangle. We've got an opposite, adjacent, and hypotenuse. And we can find out really quickly that whatever the length of this side is dependent on this angle and this side R. And we can do some simple trig. And we find out that the length of this side R perpendicular, that is just our R sine theta. Well, if that's our R sine theta, and it's based on our force, then that means that we must have a component of that force that acts this way, right? because we split this. So that's our component of the force acting that way. We'll call that our F perpendicular. Over here. So that's our S perpendicular. That is going to be F sine theta for the same reason, right? If we look at this angle, there's nothing wrong with moving F perpendicular to here. I just moved on the other side of the triangle. Nothing wrong with that. Now, if you left it over here, you'd have to do some weird things with inverting your sine cosine sort of ideas there. So the point is that we can now find an F perpendicular and an R perpendicular. So we've just set up this kind of new coordinate system. Now we also have this idea of torque. And we figured out last time that our torque is this idea of R cross F, right? The cross product of the distance to the pivot times the applied force. This cross product here, this is a vector thing. It's not simply R times it, because we have to account for this angle. That would be called a dot product. So the difference when you get into mathematics, particularly in calculus and things, you'll hear about dot products and cross products. Dot products tend to refer to things that we only care about the magnitude. Cross products account for direction. Since we're talking about torque, and our torque is dependent on this angle, we definitely are dependent on direction. So we need a cross product. This is outside the scope of the course, but if you take a calculus class and you start getting into vector mathematics, you're going to learn how to derive cross products. If you take the calculus-based version of this course, I'm going to expect you know how to do cross product. We're not doing that here. Suffice to say, this is what falls out of it. Getting your cross products is your dependence on the angle. So our cross product here, what we end up with, if this R cross F, that's got to be the same as our R, just our length to the pivot point, times our perpendicular F, F perpendicular, which is our F sine theta. That's the same thing, just like I just said, R F perpendicular, which is the same thing as R perpendicular F, depending on which one you need. So this is how we find our torque. By making these right triangle problems, accounting for the rotation with this R and this F, and using the perpendicular. So in order for the system to be in equilibrium, what we call translational equilibrium or linear equilibrium, if you like, in order for this to be in linear equilibrium, we know, just by definition, that the sum of the forces, right, the sum of these linear forces I'm talking about, has to be zero. Okay, why do we know that's equilibrium? Why do we define that as being equilibrium? That the forces, some of the forces is zero. Remember that the sum of the forces also have to be ma. If the system is moving, that means there is an acceleration at some point. The definition of equilibrium means it's not moving. So there can be no acceleration if the thing is in equilibrium. No net acceleration, right? So A has got to be zero if we're in equilibrium. So that means the sum of our forces has to be in equilibrium. So this thing is not moving in the X or the Y plane. Well, we could imagine a case where this hinge, this door, or whatever it is not doing this up and down, and it's not doing this side to side, but it's still rotating around the hinge. So in order for this thing to be totally stationary, not only do our linear forces have to be equal, we also get something called rotational equilibrium. So it's the same principle that the sum of the forces has to go to zero in order for this to work. Well, if this thing is not spinning, then it means it can't be spinning clockwise and it can't be spinning counterclockwise. In other words, if we add up all those spinning forces, they also have to be zero. Well, our spinning force, our rotational force that we've just defined as our torque. So in order for something to be in rotational equilibrium, it must have a sum of torques in the system also be zero. So these kind of problems are really what this chapter is all about. It's about creating these different equilibrium systems and then solving for them. Just like we've done all the way up to this point, though, I rarely will give you a problem where everything is nice and balanced, right? Usually what these problems are going to be about is something like, how hard do you have to pull this rope to make this door swing open at a particular velocity or acceleration or something? You're starting to kind of envision this in your head, I think. Even though I haven't showed you exactly how to solve that problem, at this point, you should have a pretty good idea of what you'd have to do to solve that. Well, it turns out that as many ways as I can ask this, there's really just three types of equilibrium problems. The first is what we call the seesaw problem. It's exactly what you think it is. It's exactly what we've shown before. This is two kids on a seesaw. You've got a pivot point in the center. You want to make a balance. This is how balance scales work. It's the seesaw problem. So we're going to learn how to do that. We've also got something called the shelf problem. So the shelf problem is the kind of thing where, let's say that we had a shelf sticks out from a wall and is suspended by some rope or chain at an angle, and then we set something heavy on top of it, TV or something like that. And we want to know how much weight we can put on that thing before that rope snaps or that chain snaps, right? So we'd like to find some tension. Again, you can think of this as a rotational problem, right? But instead of being the seesaw problem where the pivot point's in the center, Now we've got a pivot point at one extreme, but we're still doing the same thing. And the final one is called the ladder problem. So the ladder problem looks really similar to the shelf problem. They're very closely related. The ladder problem is if I have a wall, a ladder leans against the wall. What is the angle the ladder can lean against the wall before it falls down? If you've done calculus 1 or concurrently taking calculus 1, you've seen the ladder problem from a different perspective already. It's called a related rate problem. What the ladder problem is a related rate problem. We're just going to do it from a different standpoint. And that's okay. So now that we kind of have an idea of what we're looking at and the kind of thing we're going to have to solve, let's go ahead and do that. So let's set up a problem. So let's say that, just for the sake of argument, we have a wall. We have chain or something here. It's at some angle to the wall. We have some box, right? That's on the thing. We have a rope that's connecting our box to the wall. We're going to assume that this is frictionless. Okay, so we're not going to worry about friction, any of that. And so let's just set up some knowns here. So we're going to say that we know that our theta is 25 degrees, and this is a 25-degree incline. And we know that the force of tension in the rope is 5,000 newtons. So the first thing we want to do here is draw a free body diagram. So we're pretty close, right? We've already got a good start by just drawing the scene. So we need a couple more things. The thing that we know for sure is our tension force. So here's our tension force. Remember, tension is along the rope, chain, whatever it is. Important rule number 1 in physics. That's really not going to be written anywhere. It has to do with tension. That tension always acts in the opposite direction of motion. An easier way to remember that is you can't push on a rope. Compressibility works the same way. It works in the same direction. In other words, you can't pull water. Right? Water can be compressed, but you can't tension it. Rope can be tensioned, but you can't push it. So we're talking about tension. So you can't push a rope. So we know this is our tension, right? What else do we know? Well, we know that we're going to have some gravitational force. So our force due to gravity here. We also know that our gravitational force has got to have components. So we're going to label those. So this has got to be our cosine of the angle. We're again remembering our inclined plane problems. and respecting the trig, then that means that this has to be FG sine theta. So there's our free body diagram. So what we'd like to do is find out how heavy this thing is, right? Oh, there's one more force that I did not label. Oh, shit. All right. So there's one more force that we did not label here. That's our normal force, right? Always have to have the normal force. Keep my notation the same. Force normal. So we want to know how heavy this thing is. How are we going to do this? So let's think about our approach. We're going to assume that this thing is in equilibrium. Okay, so it's not going to be moving. So it's not going up and down the ramp. It's not bouncing up and down the ramp, not spinning around. Now, the equilibrium that we're concerned with then has to be dependent on the wave. So how are we going to do this? We've done tension problems before. We did this with inclined plane problems. We need to solve for this tension in terms of everything else. Because we know the tension is dependent on the weight, then that means if we know the tension and we know the angles, we can find the weight. So how can we do that? We have to assume that this whole system is in equilibrium. So we're going to say that the sum of all the forces in the x direction are zero. Okay? We're going to pick that to be our x direction. So we know that all those forces in the x direction have to sum to zero. So let's find out what forces we have in the x direction. Well, in the x direction, we can make a table, right? Forces in the x direction. That's got to be our FG sine theta. That's got to be our FG sine theta. And we also have the tension force. The only thing acting in the x direction. Well, we know that the sum of the forces has to be zero. So we can say, since some of the forces got to be zero, we just add forces, right? We have a tension force that we know, and we have to add FG sine theta. Be careful not to just do plus FG sine theta. This is not going to work for you because we have to account for direction, right? Since we can't push on a rope, the tension has to act in the opposite direction. So there must be a force pulling it this way. Well, if we call our tension the positive direction, then our FG sine theta has to be in the negative direction. So we have to use that negative sign. So that's got to go to zero because it's in equilibrium. Well, we can do a little algebra here. And we find that our tension force has got to be equal to FG sine theta, right? Moving that to the other side. Well, we know our tension force, right? That's 5,000 newtons. That has to be equal to the force due to gravity times sine of 25 degrees. If you work all this out, you will find that the force due to gravity here is 11,830 newtons. That's all we're trying to find, right? That's how heavy it is. That's the force due to gravity. I didn't ask you to find the mass, but if I had asked you to find the mass, well, since we know that the force of gravity is equal to ma, and we know force of gravity is 11,800 or 830. If we wanted to find the mass, we just divide through by A. Let's call gravity 10 just to make it easy. So divide through by 10. That means our mass is 1183 kilograms. Pretty simple, right? So why would we need to do a problem like that? Let's kind of think about a real world example. Let's say that I'm trying to load a giant flat screen TV into the back of a truck. And the truck has some ramp. And I want to pull this thing up the ramp. Well, what am I going to pull it with? Let's say the only thing that I have to pull it up the ramp with is some piece of rope. And let's say I look on the packaging for the piece of rope, or I go down to Home Depot and I buy it. And it tells me that this piece of rope has a maximum tensioning strength, or the maximum amount of weight it can hold is, let's just say it's this 11,830 newtons. Well, then I need to find out how heavy can this TV be if I'm going to use this setup. Here's something else you can do in that same scenario. Say everything remains the same, but we don't have a rope. All we have is sewing thread. Well, sewing thread obviously is not going to have the tension strength to hold this. Not one string of sewing thread. However, what if we had 100 strands of sewing thread, or 1,000, or 10,000? Well, we could do that, right? How many lengths of sewing thread would we need? Well, we need to know what the tensioning force is on the sewing thread before it breaks. We could find that experimentally, we could look it up, a number of ways. But if we find that each strand of sewing thread, let's say it can take 2 newtons of force before it breaks, then we'd have to have this number divided by 2. So you're looking at around 5,500 strands of the sewing thread that it would take to make a rope that could handle that much tension. Or even if they were all parallel, not necessarily twisted in a rope. If you twist them in a rope, you're actually going to be able to get away with fewer, because you're going to have friction between the strands of thread that's going to take up some of the energy. If we were to account for friction in this problem, it doesn't really change much, right? Let's say, for the sake of argument, this thing's going this way, this thing's moving down. It means we have a frictional force that way. So here's our frictional force. That's also in the positive direction. So this would be plus frictional force. And we know that our frictional force is mu n. So we just add it to the list, right? And we just keep adding forces. So even if we made this dependent on friction, it doesn't really complicate the problem. We're still just summing forces, guys. This is exactly what we did in chapter 2, right? Except now we're actually applying it. We're trying to do something of value with it rather than just, come up with these imaginary scenarios of here's a box on a hill. How much force it take to push the box up the hill? Well, we're actually doing something, right? We're trying to make the tension do some work for us. And we got to suspend this box. Let's look at another problem. Sort of similar. Same kind of idea. Except this time, like in this classroom, I have a overhead projector here suspended from the ceiling. So we're going to do that same kind of problem. So here's our ceiling. And on the ceiling, we're going to have two cables that are going to be attached to something. And they're going to have this kind of look to them. So that means that, oh, sorry. It helps if I finish the diagram, doesn't it? There we go. So we have some force due to gravity. And let's say that we know these angles. Let's say that one's 60 degrees. So that one's 30 degrees. So we know that this is going to be a tension force. We're going to call that tension 2. And we know this is going to be a tension force. Call that tension 1. We also know that there's going to be a force due to tension 1 in our y direction here. And there's going to be a force due to tension 1 in the x direction here. We're going to get something really similar for T2. X and y direction for those. So I want to make sure this thing is in equilibrium. It does me no good if my overhead projector is hanging from this cable assembly and swinging either left and right or backwards and forwards. So we need it to be in equilibrium. This is slightly more complex than the previous problem, but not too much. So what does it mean to be in equilibrium? The basics. We know the sum of our forces has to be 0. But this time, we're not worried about just the x direction, like we were in the previous problem, right? We were only worried about things sliding up and down the ramp. This time, we got to worry about the x and the y direction. So that means that all the forces in the x direction have to be 0, and all the forces in the y direction also have to be 0. So what are we going to do? Well, we're simply going to solve two systems of equations. So if we know, for example, let's work on the forces in the x direction first. We know those have to be 0. So let's just take a look at what we have in the x direction. The only things that we have in the x direction are the tension component of 1 and the tension component of 2 in the x direction. So we know then that our force of tension on x here has got to be equal to our force of tension from 2 in the x direction. I can do this, right? I could have just set these to 0 and then accounted for T1 being in the negative direction and done the algebra. I think we're all smart enough with algebra and problem solving at this point that I don't need to do that. So I can say that they're equal, assuming that we picked our directions smartly. We know that we have a 60-degree angle here and a 30-degree angle here. So we can do a little simple trig, and we can find out that this here has got to depend on this first tension. So that's got to be the force of tension on 1 times the cosine of that angle, in this case 60. And T2 has got to look very similar, right? That's the force due to tension from 2 times the cosine of its angle, which is 30. Well, let's find out what we can do here. Oh, one more thing. Oops, if I read my notes. Can't solve this if you don't know one more piece of information. Let's say that we've measured this, and we know that the force due to tension on that first rope on the green side is 96 newtons. Oh. Now we can just start plugging in numbers, right? So if our force due to tension of 1, that's 96. So that's 96 cosine 60. And we don't know force tension on 2, but we can solve for it. Very simply, plugging in the numbers we have so far, and we get the force due to tension on 2. It's about 54, it's about 55.5 newtons. So what did we just do? Let's keep track of what we're doing and why we're doing it. This is a common problem when solving physics problems. It's very easy as you go to solving these things to get lost in the math and to get lost in the diagrams and forget what we're trying to find. So what are we trying to find? I need to know the weight of this thing, right? We're assuming that this whole thing is in equilibrium. So in order to get this weight, this S sub G, we have to know something about all of the system. So in order to find this weight, we'd need to know something about this tension, right? Because we know that the amount of forces in the positive y direction has got to equal the amount of forces in the negative y direction. Well, that's interesting. Because if we look at the forces in the positive y direction, we have this force of tension due to 1 in the y direction, force tension due to 2 in the y direction. We can solve already for the force tension due to 1 in the y direction. So if we knew the force tension due to 2 in the y direction, if we add those together, they got to be exactly as much force as the weight. Well, let's do it. We know, since sum of the forces in the y direction is going to be 0, in the y direction, we have force due to tension 1 in the y direction, plus the force due to tension of 2 in the y direction, minus the force due to gravity. It's got to be 0. Don't forget that, right? You can't just add these together because that defeats the purpose. We're trying to overcome this gravity. It's in the negative direction, so we'll just do a minus there. That's fine. A little bit of algebra, plugging in what we know. We find this looks like the force tension 1 times sine of 60. This looks like force of tension 2 times sine of 30. That's got to all equal to force due to gravity. Well, what is FT1 sine 60? We know FT1, we were given that. We know sine 60. We know sine 30, we need to know FT2. We just found that. So we plug that in, solve for force due to gravity. And we find that the force due to gravity acting on this thing is 111 newtons. Convert that to pounds, it ends up being a little more than 200 pounds. Again, we could do the same trick, finding the mass. If we divide it through by the acceleration due to gravity, we'll get the mass. In this case, it ends up being around 10 newtons. So, or 10 kilograms, sorry. Just another equilibrium problem, right? Look at the difference. There's this problem. This class gets a little more interesting. These are all what we call static problems, by the way, or statics. You could take an entire class in engineering called statics. An example of a problem you might find in an engineering class is, let's say that we have a bridge. We know the distance between the pylons, maybe it's a river or something down here. And we have a bridge that we want to build, a road. And we know that the road needs to support a certain amount of cars. So let's say this looks something like the bridge going into Memphis. Have you ever been over that way? The Memphis Bridge has this very distinct look. Has these arches like this. So why are those arches there? Well, it turns out those are there because if you just built this straight road, it would not be able to support, it wouldn't support its own weight, for one, because it's all asphalt, concrete, steel. And it certainly wouldn't be able to support the weight of all the traffic. If you want to test this yourself, get yourself a piece of plywood and a couple of cinder blocks. The further apart you move the cinder blocks, the more sag you're going to get in that piece of plywood. Or you can put more people on the plywood if you want, and eventually it's going to break. You don't want that to happen on the Memphis Bridge. This actually was a problem last summer, right? If you guys were here last summer, you remember this. They had to shut that bridge down for a couple of months because they found a stress fracture in the support of the bridge, which is dangerous. So we had to fix it. So the problem you do in statics is you have this kind of bridge, but then what you do is you start looking at some of the forces. So before we do the archway problem, the other kind of bridge construction you see looks like this. It has these kind of trapezoidal things. And you might have some support beams in there. And so what you do with this kind of problem is you find the total force, or the total weight you want this bridge to hold. So the weight of the road, plus all the maximum level of cars you might want, plus another 300% for a safety factor. And then what we do is we start calculating the force on each of these beams. But we also have these. We have this one, whatever they are, right? That's all going to depend on all these angles. And so that's what you're going to do in a statics class, is you're going to work through these big complicated systems like this. So the reason that bridges look like that is because we're distributing the weight. All we're doing is an equilibrium problem. If you're a civil engineer, this is your life. If we have a case like the Memphis Bridge that has these arches, this gets into some more calculus. This is why we don't do this in a basic statics class. That now this depends on the radius of that arch, and you need calculus to solve that. But you do it exactly the same way. You just sum the forces, but instead of doing basic algebra and arithmetic, we do it with calculus. And we sum across all possible positions of R. So we get to integrate, and it gets messy. But this is the reason that we would do problems like that. I'm not going to give you anything nasty like a bridge problem like that. Don't worry about it. But I wanted you to see how it works. Let's do one more of these statics problems and then I'll move into work. So let's do this. Here's some shelf. On the shelf, we have a box that weighs 15 kilograms. And we know that the box is going to have a rope. That connects to a wall. Let's say the angle it makes to the wall is 30 degrees. And out here, we have another box of mass M that hangs at this pivot point. And we'd like to know what the mass of the box is. So, how are we going to do this? Not really all that difficult. We need some forces. So let's start labeling things. Let's assume that there's some friction between the box and the shelf. We know that there's going to be a tension. Now, because we have another box out here, at some point, the direction of the tension is going to shift. But we know that they have to be the same, right? Because it's not possible to have this one rope under tension where it has some tension on one side and then arbitrarily a different tension on the other side. So those two have to be the same. We also know, since this box is in contact with this shelf, it has some normal force. And we know that it has some weight. We call that weight 1. Now over here, that box also has some weight too, but notice there's not a normal force. They're not in contact with anything. Well, let's first of all start finding what we can find. This is all we know, right? So from this, we're going to be able to find the mass of that box. This is one of those physics problems where you are not going to be able to solve this in one step. This is going to take work. Just like our problem from the second test with the race car, and I asked you to find its kind of trajectory and treat it like a projectile when it flies off. And we had to solve one piece to get something to solve a second piece, to get something to solve a third piece. We're going to do the same thing. So if we start looking from right to left here in this diagram, we find very quickly that we don't have any way to find that. There's a lot of unknowns. So let's start with what we do know. We know a mass. We know there's friction. And we're going to say arbitrarily that the coefficient of friction between the table and the box is 0.27. Remember, that's a coefficient, so it's units. Well, since we know that, we can find the tension or the frictional force very easily, right? We know that friction is mu times the normal force. Well, what's the normal force? F sub n. It's got to be equal to this weight, right? And so we know the weight of that thing is just mg. So the frictional force has got to be mu times m times g. We know mu 0.027. We know mass is 15, and we know gravity is 9.81. Again, dropping the units because I'm going to trust that you guys know how to do dimensional analysis at this point. So what we find is that we have a force due to friction. Remember, it's a force, so it should come out in the newtons. And in fact, it will. So if you work this out, you get a value of 39.69 newtons. That is our frictional force. At first glance, it might seem that that is useless. Well, what do we know? What are we trying to find? We're trying to find this mass. What's the other big assumption that we're making about this system? We're assuming the system is in equilibrium. If we assume the system is in equilibrium, then that means that our X and our Y component forces all have to be zero. Now, some zero. Not that the forces themselves are zero, right? Clearly, that's non-zero. Clearly, there's some tension. But look at what else is in the X direction. Nothing. We have the frictional force and the tension force. And we're just looking at this object. So we can treat this as two different problems, right? So we're looking at the friction force and this tension force. If these things have to be equal, well, we know that the frictional force has got to be equal to that tension force. So we know that our tension force is 39.69 newtons. Ah, now we can start doing something interesting. Now let's look over here. So this rope has to have some other tension, right? Because there's this pivot point, so it's not restricted now. Well, if that's true, then there has to be an X direction, and there has to be a Y direction. So let's go over and look at this system, right? So we looked at this system. Now we're going to look at this system. And let's see what we have. We know it's in equilibrium. So what does that tell us? That all the X forces have to sum to zero. So what X forces do we have? We have T1 and T2 in the X direction. Okay. So that means that T1 has got to equal T2 in the X direction. We know what T1 is, right? We just saw for that. That's going to be 39.69 newtons. We want to know what T2 in the X direction is. Well, T2 in the X direction has got to be the total magnitude of T2 times the cosine of 30, because we know that's 30 degrees. So what did we just find? We found that T2 is equal to 45.8 newtons. We're close, right? So we've just balanced all the forces in the X direction. Now we have to balance all the forces in the Y direction. Well, what forces do we have in the Y direction? We have weight 1, weight 2, and the normal force in the first box. Right away, we know that the weight of 1 and the normal force are going to cancel each other out. They have to. So what are we left with? We're left with this system, and the only Y thing that we don't know is W2. And what were we asked to find? We're asked to find the mass of this. So how are we going to do this? Very simple. We sum the forces again, right? It's just an equilibrium problem. So we know that our W2, that's got to equal our tension of 2 in the Y direction. Well, our W2, we know that's just mg. And our T2 in the y direction is the total magnitude of T2 times the sine of 30, again, trig. All right, well, we don't know mass, let's try to find. G is 9.81. What's T2? We just found that. That's 45.8. And sine of 30 is whatever sine of 30 works out to be. Solve for this. And what we end up with is something that's 2.34 kilograms. That's exactly what I wanted to find. Nothing overly complex, right? T is yes. Long yes. But not complex, not hard. Slow down and take your time. All we're doing is solving different systems of equations. So let's make this more interesting. Let's do something. Wish you guys were actually in this classroom with me, because I have 3 whiteboards that you can see on either side of this classroom, as well as these 3 or 4 that I can manipulate here. So when I teach in this classroom, normally I will cover all the whiteboards at once. And it's glorious. Actually, what I like to do in this class is I don't cover all these whiteboards at once, you guys do. Generally, what I would do in a class like this is I would split you up into groups of a couple and give you each one of these problems and go, figure it out. And then I walk around and guide you. But since we don't have that luxury here, I have to do all the heavy lifting, as usual. So here, let's say that we have a nut, and we put a wrench on the nut. And let's say that my wrench is 35 centimeters long. I apply some force. And I know, let's say that I have measured this, and I find out that the torque that it takes to make this nut move is 45 Newton meters. That seems like a really strange unit of measurement, right? It's a force. So we're used to seeing forces written in newtons, but remember, this is torque. It's not a traditional force in the way we've been thinking about it. It has to do with rotation. And it's dependent not only on the applied force, but also this distance away from the pivot. So we get a unit for torque that's the Newton meter. You have probably heard a torque measurement before, but not in terms of Newton meters. You've probably seen ads for trucks or cars or something that talk about how much torque the engine has. Usually it's horsepower or something. Or a lot of times they'll talk about inch pounds of torque or foot pounds of torque. It's the same thing. So foot pounds is backwards. So it'd be distance times force. So our distances in feet are forces in pounds in the imperial or the freedom system. So you get foot pounds or inch pounds. You might have heard of or used a thing called a torque wrench. It's a wrench that is used to tighten bolts to a very specific limit. I use them all the time. I was working on airplanes. And the reason you'd ever want to do that is because there's going to be some limit at which point you can turn this bolt or this nut so tight that it breaks. Or it has to be at some minimum limit in order to make a good seal, a good connection between whatever two things that you're bolting together. So the way a torque wrench works is you have a pivot on your torque wrench. And that pivot is just a hinge, and it has been calibrated at the factory such that you overcome, there's basically a spring in here. You overcome the spring tension at a certain amount of applied force. And if you know the distance between the handle and the hinge, then you can set a spring that requires a certain amount of force before it bends. And so in a torque wrench, what you do is you take your torque wrench that says it's calibrated for 120 inch-pounds. You put that on your bolt and you start cranking it. As long as you don't exert more than the amount of force required to get this thing to 110 inch-pounds, it'll turn. But as soon as you exceed that amount of force, that spring will release and the whole handle will kind of bend a little bit and let you know you've reached your limit. Some torque wrenches have adjustable limits that you can put on them. And the way they do that is they have a knob at the end of the wrench that you can turn. It's just on a screw. And what it's doing is changing this length by small amounts, right? By fractions of an inch. And so you can dial in torques. And so you'll see these kind of torque wrenches are a little more expensive, and they'll have a range. It'll say this torque wrench works between 50 inch-pounds and 1,000 inch-pounds. I mean, hell of a big torque wrench, but and then if you use these in industrial settings like aircraft maintenance, you have to send these to be calibrated on occasion because through wear, obviously the spring will wear out, that kind of thing. And you want to make sure that it's giving you the right tension that you need. So here's this problem. So we have a wrench. We know how long the wrench is. And we know how much torque it takes to break this loose. So I need to know how hard do I need to turn the wrench or pull it or whatever I'm going to do, right? Well, I know the torque. I know that torque is R cross F. So I need my R and I need my cross F. So I need to know something about that angle. Conveniently, I'm going to pull on this thing at a 90-degree angle. So I've only got really sine and cosine to worry about, right? Need this component. That's going to be my sine. My cosine gives me the component along the wrench, which does me no good, right? It doesn't do any work. So that's got to be the sine of my angle. In this case, 90 degrees. Sine of 90 is 1. So that gives me my 45 Newton meters. Since the sine of 90 is 1, and I know R, careful, this is in Newton meters, this is in centimeters, so you need to do some unit conversion. So we know that R in meters is 0.35 meters. So that's what we're going to put in here because remember, everything has to be the same. So 0.35 times whatever this force is, sine of 90 is 1, so that goes away. And that's got to work out to be my 45 Newton meters. So if this is meters, this is in Newton meters, meters cancel, we're left with newtons. And so if you do the math here, You end up with 129 newtons. I think that works out to be about 240 pounds or something. Which is a lot. So that's torque problem. Find out how much force you need to break that nut loose. You'll see sometimes at hardware stores, and if you're doing kind of maintenance, a lot of times you'll see something they call Loctite. It's a goo that you put on a screw or a nut to make it stay in place. Basically, what you're doing with that is, in addition to your screw, what you're doing is you're adding friction with this Loctite stuff. So not only do you have to overcome this torque, you also have to overcome the friction that's fighting you. So you're increasing the amount of torque you need. So if you have a bolt that needs to be able to withstand 200 Newton meters of torque, and you put Loctite on it, it'll really hold up to like 1,000 Newton meters of torque. It ain't coming loose. There's a really cool meme that I've seen that shows a bolt and a guy with a screwdriver, little short stubby screwdriver. It says come off. And then the next one is the same bolt with a dog bone wrench or something. And it says please come off. The next one is a guy with this huge long lever and pipe wrench. It says I wasn't asking. And then the last frame is a bolt with somebody putting a blowtorch on it and it's turning molten. And it says it can't be tight if it's liquid. So this is aircraft maintenance 101, by the way, if you guys go to aircraft maintenance. This is also, interestingly enough, the basis for something that Archimedes said. Archimedes, famous scientist in ancient Greece, gave us Archimedes' principle. Archimedes' principle is the thing that talks about if you submerge an object in a liquid, the amount of liquid displaced is equal to the mass of the object submerged. The story that may or may not be true that goes along with that says that Archimedes was summoned by the king because somebody had given the king a crown and said, this is made of pure gold. And the king said, not sure I believe you. So he calls Archimedes and he says, Archimedes, I want you to find out if this thing is pure gold, but don't destroy it. Because if it is pure gold, I want to keep it as it is. So Archimedes is trying to solve this problem. And one day he's in the bath and he's got this crown next to him and he picks the crown up and he's examining it. He's thinking, how am I going to do this? But he notices that as he picks the crown up, the water level in the bathtub rises. When he puts the crown down, the water level in the bathtub goes down. He thinks, this must be because of the extra mass. So he gets out of the bathtub, just a bathtub full of water. He puts the crown in there and the crown displaces the water. He does some calculations, he measures the amount of displacement, compares it to what he knows to be the density of gold. Says, this is how we measure density and displacement. So he gets very excited. So remember, he's just got out of the bath, he's butt naked. He runs through the streets of Athens screaming, Eureka, Eureka, which is Greek for, oh my God, I'm naked. I think it means I found it, actually. I like to think it means I'm naked. So Archimedes also came up with another clever saying. He said, give me a lever long enough and I can move the world. Let's think about what that looks like. So here's the Earth, as viewed from above, because as we all know, the Earth is flat. So the Earth as viewed from above, our flat disk of an Earth. If you put it on its side, you can see the turtles. Archimedes proposes that if I have a lever long enough that I could move the Earth. So let's imagine what that looks like. Let's just take a lever and we apply some force. At some point, we're going to create enough torque that we can cause this to displace. Let's say I know the mass of the Earth. Oops, the mass of the sun. Mass of the Earth. This is a symbol in astronomy. The circle with the plus in it, that's Earth. The circle with a dot in it, it's the sun. So let's put an imaginary pivot here at some distance r. Well, we know the mass of the Earth. We have to be a little apocryphal here, and we have to make a big assumption. We have the mass of the Earth times the gravitational acceleration of the Earth. In astronomy, that's not going to work because everything is attracted towards the center of mass, which is what gives you the acceleration due to gravity. But if we're talking about the entire planet, there's nothing that attracts it. But we're going to assume that we can somehow measure the weight of Earth. And it's kind of a nonsensical thing, but the weight of Earth on Earth would be its mass times acceleration due to gravity. So we know that those two have to be the same. So this r cross f, so whatever this angle is, right? So this will be f r cos theta, and that's got to be equal to the mass of the Earth times the acceleration due to gravity. Well, if we know this, the mass of the Earth times acceleration due to gravity, we need to know the distance and the force. Well, let's think about what Archimedes said. Let's take him at his word. And he said, give me a lever long enough and I can move the world. So we're going to assume that this is a reasonable amount of force for a person to apply. Well, I assume that, like me, since he was somewhat of a physicist himself, that Archimedes is pretty lazy. So he probably doesn't want to exert a whole lot of force and a lot of work, right? So let's just say, for the sake of argument, that we wanted this force to be 10 newtons. Pretty low. Okay, now we know a force that we want to apply. We know the angle. We can pick that, right? Because we can make this whatever we want. Now, if we want to find that angle, well, it depends on where this pivot point is. So if we set the pivot point up at, halfway between the Earth and the moon, let's say, and we're standing on the moon doing this, we can do some simple trig and we can find that angle. In a problem like this, I'd probably give it to you. So we can plug in that angle, we can plug in this force, and we solve for R. Now, if you do this, you will find that even if you are able to exert a force that is roughly equal to the mass of the Earth times acceleration due to gravity, even if you're able to approach that force over on this end, that the length of this pivot arm has to be something like the length of the Milky Way galaxy. It's about 100,000 light years across. If you go to some ridiculously low amount of force, like 10 newtons, then it turns out that this length of this rod has to be longer than the width of the observable universe, which is about 13 billion light years. So Archimedes, while technically correct, which is the best kind of correct, was onto something, but couldn't be done in reality. What is this? This is the seesaw problem, right? The seesaw problem is just the two balance points across a pivot. That's what we're doing. Just the torque problem. And you can see how very easy these are to set up if you draw them correctly. Even this big complicated thing here. We had what looked like a reasonably complex system of two masses. We had this kind of weird tensioning system set up. And we knew very little information, right? We knew what this coefficient of friction was, and we knew how much that thing weighed, just using the power of physics. Oh, and we knew this angle. Just using the power of physics, pretty rudimentary physics, we can relatively easily find the mass of that. So this is very useful, right? Next time you go to a concert or something, look at the lighting systems they have around the stadium, and you'll see this. The longer you study this stuff, the more you start to see physics everywhere. Look at cars driving down the road, you're going to see rotating wheels, and you're going to think about angular velocities. Look at the ceiling in this classroom, has these, what's called a suspended ceiling. And so you have these tiles on these suspended frames, and you can start to see, oh, I guess that tells me how to build that. So again, statics, equilibrium. This is civil engineers, what they do all day. Build bridges, build structures. What we do. A lot of this comes into play later on too. This is not just mechanical forces. In physics 2, if you happen to take physics 2, what we're going to do is we're going to say these are no longer masses. We're going to say these are electrical charges. So these are electrons. And we want to know what kind of attractive or repulsive forces that the electrons feel. We're going to use exactly the same techniques. It's actually pretty cool. There's a huge correlation that most students miss until about the second or third time through electronics or electricity and magnetism. There's a huge correlation between the mechanical force equations and the electric force equations, because they're all just forces. Just like we're seeing here. We started this semester with just the static free body diagram system, and we learned how to sum forces. And now we've moved on to, okay, now that we can sum those forces, let's do something with it. What does it mean if the forces are summed? What if this wasn't in equilibrium? What if I knew this thing, this block over here, was actually moving downward at some velocity? Well, now it's not static equilibrium anymore, right? Now this thing is moving down with some velocity, which means this thing is going to be traveling with some velocity. So instead of assuming the sum of the forces are 0, the sum of the forces have to be MA of the whole system. And if we assume an acceleration, then that means there's got to be some delta V. And delta V is what we started with. So we could back into finding the velocity at which that thing was moving. And if I know the velocity that it's moving, and I know the length of this table, I can tell you how long it takes for this thing to slide off the table. So not a huge leap to get there. and you guys are progressing well. I think that is enough for this lecture. I encourage you, as you finish that homework, I encourage you to read through the Chapter 9 notes that are now up on Blackboard. I encourage you to get a lot of practice. Go out and search static equilibrium problems and torque problems, and you will find enough to keep you busy for years. In fact, that's where I found these examples. I didn't feel like making them myself, so I just Googled some. So I encourage you to work this, because even though I know when I'm doing this in class, this looks easy. And as I lecture, you go, oh, that's trivial, I can do that. And then when you sit down and try to do homework, you go, I have no idea what I'm doing. The only way to get better is just practice at it. So I would strongly encourage you to go look at some examples of stuff I didn't get to. Seesaw problem, you might want to get a couple of examples. Look at the ladder problem, couple of examples. They all solve the same way, some of the forces. Right. So having said that, remember, I'm out, so no live lecture Friday. I will post supplementary videos for you guys for next week, as well as a homework assignment that I'll expect you to work through. And then when I return, we will continue on with the rest of the semester. So see you guys then.